This lecture is the second part of the Black Zero Brain of BFS S10. In the first part, we studied the theory from the gravity side, 11-dimensional supergravity and its M-wave solutions, whose dimensional reduction gives rise to the Black Zero Brain of type 2a supergravity. In this second part, we turn to the gauge theory side. We will focus on the tests of the gauge-gravity duality and the matrix physics origin of Hawking radiation of the Black Zero Brain within the BFSS10 model. The BFSS matrix model plays two central roles. First, it provides the discrete light cone quantization of M theory, giving a non-perturbative definition of 11-dimensional quantum gravity. In this sense, BFSS is the microscopic theory from which spacetime and gravity emerge. Second, it serves as the gauge theory dual of the type 2a Black Zero Brain, a thermal supergravity background describing a bound state of ND0 brains. Through this duality, the BFSS model connects the quantum mechanics of matrices to the thermodynamics of black holes. In the previous lecture, we analyzed the system from the gravity side. Starting from 11-dimensional supergravity, we reduced the M-wave solution to 10 dimensions, obtaining the Black Zero Brain geometry. We then computed its thermodynamic properties, temperature, entropy, and energy, first in the classical limit, and then including the R to the fourth quantum gravity corrections. These results gave us a complete analytic description of the Black Zero Brain thermodynamics derived from the M-theory side. In this lecture, we turn to the gauge theory side of the correspondence. Our goal is to compute the same thermodynamic quantities directly in the BFS S10 matrix quantum mechanics and compare them with the gravity predictions. We will explain the core-tail separation in the extent of space and the E of X procedure used to extract the energy of the bound core. We will then discuss the origin of flat directions, their connection to Hawking radiation, and how finite N effects in the BFSS model reproduce the mechanism of black hole evaporation. The ultimate goal is to perform a quantitative test of the gauge-gravity duality and to understand within this dual framework the microscopic mechanism of Hawking radiation. We move then directly to the duality side of the correspondence. The BFSS matrix model provides the gauge theory dual of the Black Zero Brain geometry we have analyzed on the gravity side in the previous lecture. This duality connects classical solutions of type 2a supergravity with strongly coupled quantum mechanics of D0 brains. We give in equation 27 the Euclidean action of the BFSS model. It is a 0 plus 1-dimensional supersymmetric gauge theory with 9 bosonic matrices XM and 16 fermions psi alpha, all in the adjoint representation of UN. The first term represents the kinetic energy of the matrices, the second is the commutator squared potential, and the last two terms describe the fermionic kinetic and Yukawa interactions. Physically, this theory captures the collective dynamics of N-coincident D0 brains, the microscopic constituents of the Black Zero Brain. Equation 28 shows in fact the corresponding type 2a supergravity background, the Black Zero Brain metric. It depends on two functions. The blackening function f of u equals 1 minus u0 to the power 7 over u to the power 7, and the harmonic function h equals lambda times d0 over u to the power 7, with d0 is a numerical factor. Here, lambda sets the horizon curvature. Large lambda gives a smooth classical geometry. Small lambda pushes the system into a string-dominated quantum regime. We now summarize the duality statement that underlies the entire correspondence between the BFSS matrix model and the Black Zero Brain. The two descriptions, the gravitational and the gauge theoretical, represent the same physical system, viewed from opposite limits of the coupling and number of colors. The parameters u0 and lambda on the gravity side correspond respectively to the energy scale, and T-Hooft coupling constant lambda equals gym squared times n of the BFSS quantum mechanics. On the gravity side, classical type 2a supergravity describes the Black Zero Brain solution in the limit of large n and large T-Hooft coupling lambda. On the gauge side, this corresponds to the strongly coupled regime of the BFSS quantum mechanics. Quantum gravity corrections on the supergravity side, those arising from loops in the string coupling GS, are dual to 1 over n squared corrections in the BFSS model. In this sense, the finite N-gauge theory provides a complete, non-perturbative definition of quantum gravity in this sector. Equations 30, 31, and 32 summarize the thermodynamic relations for the black zero brane obtained from supergravity. These scaling relations are the classical supergravity predictions that will be tested quantitatively against the results of the BFSS model. Moreover, we can also give the quantum gravity-corrected thermodynamics in a compact form. From the 11-dimensional effective action, the entropy scales as T to the 9/5 with a subleading term proportional to epsilon times T to the minus 3/5. Equivalently, the energy scales as T to the 14/5 with a negative subleading term proportional to epsilon times T to the 2/5. The numerical coefficients encode the one-loop R to the fourth correction computed earlier, and all subleading pieces are proportional to epsilon or 1 over n squared. Differentiating gives the specific heat, a positive leading term proportional to T to the 9/5 and a negative 1 over n squared correction proportional to T to the minus 3/5. At sufficiently low temperature, that negative correction dominates and the specific heat turns negative, signaling the onset of the Hawking evaporation instability. In the large n limit, the correction vanishes, and the classical, thermodynamically stable black zero brane is recovered. We now test the gravity predictions directly in the gauge theory using finite n Monte Carlo for the BFSS model. First, the energy density is measured as E over n squared. The energy is defined thermodynamically by E equals minus the derivative with respect to beta of log z, with the partition function z given by the path integral over matrices and fermions with weight E to the minus s BFSS. This provides a direct gauge theory observable to compare with the black zero brane energy. Second, we monitor the extent of space, written r squared. It is the thermal average of the matrix size. R squared equals 1 over n beta times the integral from 0 to beta of dt of the trace over the sum from m equals 1 to 9 of xm squared of t. Operationally, this quantity tracks how widely the d0 brane eigenvalues spread. In simulations, the histogram of r squared has a sharp peak, the bound state or black hole core, and a long tail from runaway eigenvalues, which we interpret as Hawking radiation. At small n, the tail is prominent and the system tends to evaporate. At large n, the tail is suppressed and the bound phase dominates, matching the classical supergravity limit. The way we measure energy in the BFSS model is crucial because it determines how we isolate the bound black hole phase from the unbound, radiating configurations. To observe the finite n effects corresponding to quantum gravity corrections, we analyze the energy at sufficiently small n. In the simulation, each Monte Carlo step generates a configuration of matrices xm of t. For that configuration, we compute the extent of space, r squared of x. The histogram of r squared typically shows a sharp peak representing the compact bound state of d0 branes, and a long tail describing configurations where eigenvalues have escaped, the analog of Hawking radiation. To focus exclusively on the bound phase, we introduce a cutoff parameter x. At each Monte Carlo step, we test whether the configuration satisfies r squared less than x. If the condition holds, we include that configuration in the calculation of the energy for that step. After many steps, we compute the average energy, denoted E of x, and normalize it as E of x over n squared. This defines the energy restricted to the region r squared less than x. By varying x, we can distinguish between the bound and unbound regimes. For small x, we measure the core energy of the bound state. As x increases, we begin sampling the tail. When E of x saturates to a plateau, the result becomes independent of x, indicating that the true bound state energy has been reached, since it is insensitive to the tail, for that set of temperature T, matrix size n, and lattice size lambda. Finally, we eliminate any residual cutoff dependence through the extrapolation E of lambda equals E plus c over lambda, and take the limit lambda goes to infinity to obtain the continuum value of E over n squared. This method isolates the intrinsic energy of the black zero brane from the Monte Carlo data and allows a precise comparison with the gravity prediction. The final result, obtained by Hanada, Hyakutake, Ishiki, and Nishimura in 2013, is shown in equation 40 and matches precisely the gravity side prediction, confirming the gauge-gravity duality at the quantitative level. In summary, the distribution of r² measured in the Monte Carlo simulation is sketched in this histogram. The sharp peak corresponds to the compact, non-commutative bound state of D0 branes, the black hole core, while the long tail represents configurations where some eigenvalues have escaped along the flat directions, the gauge theory analog of Hawking radiation. By isolating the peak region, we have extracted the intrinsic energy of the bound state and compared it with the gravity prediction, achieving a direct, numerical verification of the black zero brane thermodynamics. The BFSS potential is minus trace of the commutator squared. Whenever the matrices commute, commutator xn equals 0, the potential vanishes and there is no restoring force. These commuting configurations define the flat directions. When the xm commute, they can be simultaneously diagonalized. Their eigenvalues are the spatial positions of the D0 branes. Along flat directions, D0 branes can drift arbitrarily far apart without cost in potential energy. This motion corresponds to D0 branes escaping from the bound state, the gauge theory realization of Hawking radiation. The black hole core is the region of non-commuting matrices with clustered eigenvalues. The radiation tail is the region of commuting matrices with separated eigenvalues. At large N, collective effects from non-commutativity generate a strong binding. Typical configurations are non-commuting, eigenvalues remain clustered, flat directions are tamed, and the black hole is stable, matching classical supergravity. At finite n, 1 over n squared fluctuations enhance motion along flat directions. Eigenvalues drift apart, runaways appear at small n, and the bound state becomes metastable. This is the microscopic, matrix model picture of Hawking evaporation. We can now ask, what does all of this really mean for quantum gravity? From the gravity side, the thermodynamic scalings and the subleading corrections, the 1 over n squared and alpha prime terms, are genuine predictions of M theory and type 2a supergravity. From the gauge side, the finite n Monte Carlo results of the BFSS model provide an independent, non-perturbative verification of those predictions. The two match precisely, both in scaling and in numerical coefficients, establishing one of the most direct and quantitative confirmations of the gauge-gravity duality. In this context, quantum gravity is not a separate theory. It is simply the finite n completion of supergravity, the regime where spacetime itself becomes dynamical within the matrix model. The test remains sectorial, near-extremal D0 branes, large coupling, thermal, and Euclidean, but within this window, it provides a controlled, quantitative verification of quantum gravity from first principles. In summary, we have shown that the black zero brane thermodynamics, derived analytically from M theory and verified numerically from the BFSS model, represent a concrete, testable realization of quantum gravity in the laboratory of matrix theory.